Hello friends, welcome back to my YouTube channel. In this class, I am going to discuss about the entropy. How entropy is a property of thermodynamic system. Just like your energy, volume, temperature, pressure, entropy is a property of system. In fact, thermodynamic system. How to prove that? And how this can be obtained from clausius inequality. In the last class, I have discussed about the clausius inequality. So now I am going to prove how I want to prove that entropy is a point function or property of system. Before starting, I must say one thing to all of you. Please do subscribe to this channel. Of course, like it and share it to your friends. So let's get started. You see, in Clausius inequality, this is the Clausius inequality. Cyclic integral of del q by t is less than or equal to 0. You see, this Clausius inequality is valid only for cycles, both for reversible as well as irreversible cycle. In fact, the equality, that is cyclic integral of del q by t equal to 0, is valid only for internally reversible cycle. Internally reversible cycle. Internally reversible cycle or totally reversible cycle. Totally reversible cycle. And you see this inequality, cyclic integral of del q by t is less than 0, is valid only for irreversible cycle. Irreversible cycle. So you see, cyclic in this equation, you see, this is suppose the equality part of the Clausius inequality, and this is the inequality part. It's valid only for a irreversible cycle. But what about this equality? Cyclic integral of something is 0. Cyclic integral of which quantity is 0? That we must first understand in thermodynamics. What is that quantity of which the cyclic integral is 0? For example, suppose there is a certain amount of gas in a cylinder bounded by piston. This is the cylinder piston arrangement, and some amount of gas is inside this system, and initially the volume is suppose 5 meter cube. Volume of gas inside this cylinder, and which is bounded of course by piston. So this system's volume is 5 meter cube at state 1. Suppose this is your state 1. And somehow if we expand the gas, if the system is expanded, its volume may increase to suppose 8 meter cube. And this is suppose state 2. Since at least one of the properties of a thermodynamic system has changed, means a state change has taken place. So if suppose this system is once again compressed, if this system is once again compressed, suppose if this system is once again compressed to its initial volume, that is 5 meter cube, then this is suppose this is again it comes back to state 1. That means initial state. Here in the initial state, the volume of the system was, thermodynamic system was 5 meter cube, and it expands to 8 meter cube in that is another state 2. It comes to another state 2, and once again it comes back to initial state. So these two processes constitute a cycle. So if you plot that on a process diagram, you will see that suppose this is 1 2, again this is 2 1. Initial system completes a cycle. So cycle means, you see, this is your cyclic integral of dv. You see, dv means differential of volume, that is equal to delta v of cycle, delta v of cycle, which is nothing but 0. When a system completes a cycle means all its properties regain the initial values. So that's why cyclic integral of any property is equal to change in the value over that cycle. So whenever a cycle has been completed, all its properties come back to its original state. So that's why delta v of a cycle during a cycle, change in volume during this cycle is 0, and change in fact any case of property, be it energy, be it temperature, pressure, the cyclic integral of any property is 0. But from this is, we don't know whether it is a property or not. Del q by, what is del q by t in fact? But what we found is cyclic integral of this quantity is 0. So this must represent a differential form of property, just like dv, because cyclic integral of dv is 0. So if this cyclic integral of this quantity is 0 means that must represent a property, that must represent a differential of any property. Since cyclic integral of dv is 0 and this property we don't know, up to now we are not aware of that property, so I can say cyclic integral of del q by t is differential of a property, suppose x. What is the property x? We don't know up to now. So the same results can also be derived if we analyze over a process diagram. If we analyze over a process diagram, you see, suppose this is the PV diagram and a system is taken from an equilibrium state I. Suppose I is an equilibrium state and system is taken from initial equilibrium state I to final equilibrium state F following a reversible path. You see, this is in fact applicable for reversible cycle only. This is reversible cycle only. So this property is only valid for reversible cycle. So reversible path only. Cyclic integral of del q by t is cyclic integral of a dx, and this is valid only for reversible cycle. That means del q by t is definitely equal to dx, differential of property. Suppose this is let a system be taken from initial equilibrium state I to final equilibrium state F following the path, suppose R1, and then suppose it comes back from state F, equilibrium state F, to I following another reversible path R2. In fact, these two reversible paths constitute a cycle. We know that these two reversible paths constitute a cycle. So from clausius inequality, in fact, we know that cyclic integral of del q by t, or you can say d cot q by t, both are same thing. So cyclic integral of d cot q by t is equal to 0. So that means, or I can say cyclic integral of d cot q by t is nothing but the integral of dq by t along the path R1 plus dq by t along the path R2, because these two paths R1 and R2 constitute the cycle. So that means d cot q by t R1, suppose the system has traveled from state I to F following the reversible path R1, then it travels from F to I following the reversible path R2 is equal to 0. Cyclic integral of d cut q by t is nothing but the summation of d cut q by t taken over all the paths that constitute the cycle. This is equal to 0, or I can write like this: is equal to minus of R2. And since R2 is a reversible path, and according to the property of definite integral, this equal to, I can write, integration limit is from I to f d cut q by t, d cut q by t. And this is valid because R2 is a reversible path. That means if a system can travel from f to I, means a system can also travel along the reverse path, that is from I to f, since it is a reversible path. Had it been an irreversible path, this thing would not have happened. So what we found is integration of dq by t from I to f is equal to integration of dq by t from I to f, but paths are here different. So this quantity here, whatever value you will find along the path R1, the same result you will find also if you integrate along the path R2, because the states are same. So this quantity, that means this quantity is independent of the path, and it depends only upon the end states, that is I and f. These values are equal just because the initial and final states are same. Although paths are different here along the path R1, and this is another path R2 which connect the same two states I and f. So the value, that means what we conclude is this quantity is independent of path and dependent on states only. So we know that this is point function, just like your volume, energy. So since this is not a path function, only in thermodynamics we have already discussed work transfer and heat transfer as path functions. So from this analysis, what we found is that integration of d cut q by t limit from I to f along path R1 is equal to integration of d cut q by t along path R2. So this is definitely, this must represent a differential form of property. So dq by t is equal to dx, dq by t is equal to dx. And what is this x? Actually we are going to discover it. And since this is independent of path and it depends upon end states only, so it is a property, just like your volume. Suppose a system travels from state 1 to 2. This is state 1 and volume is suppose v1, and this is state 2, volume is v2. Whatever paths you may take, even along this path, if system travels, change in volume is v2 minus v1. And if the system travels along this path also, the change in volume is v2 minus v1. Whatever path the system may follow, the change in the value of volume will remain same, and that will be independent of path, just because volume is a property. Similarly, since this quantity is independent of path and depends only upon the end states, that is initial and final states, that is I and f, so that's why this must represents a differential form of property, and that property suppose x. And Clausius in 1865 named this property as entropy, and entropy, which is usually designated by capital S, and in fact it is defined for a reversible path. Integral of dq by t along a reversible path integration can be done only on a reversible path. And if you integrate this will be, in fact, delta s, and this will be SF minus SI, and this is in fact an extensive property. This is total entropy or extensive property, and its unit will be, obviously unit of heat transfer is kilojoule and unit of temperature is Kelvin, so unit of entropy will be kilojoule per Kelvin. So there is a physical significance of entropy which we will discuss later on, but this is how the property was developed by Clausius in 1865 in fact. And so cycle integral of d cut q by t is equal to SF, the total entropy or entropy only at final state minus total entropy or entropy at the initial state. And if you divide extensive property and calculate for unit mass, you will get specific entropy. So this unit will be unit of specific entropy will be kilojoule per kg Kelvin or joule per kg Kelvin. So this is, but this, the one important point is that this property integral of dq by t can only be calculated along a reversible path, and this property definition of property is valid only for reversible path only. Reversible path. Suppose a system has traveled from state I to initial state is suppose I and final state is suppose F, and the system has traveled from initial equilibrium state I to the final equilibrium state F following an irreversible path or actual path. This is actual path. You know, reversible process, reversible path is just ideal case. So how to find out the change in entropy during this process? That's another question that is to be answered. You see, system has traveled from initial equilibrium state I to final equilibrium state F along an irreversible path. So how to find out the change in entropy? So we cannot apply this formula here, because this integration can be carried out only for reversible path. This property is defined ds is equal to d cut q by t. That's why it can be written like this. This is valid only for this. That means whenever heat is added to a system in a reversible manner, or heat transfer takes place in a reversible manner, then only ds is small change in entropy, that is equal to d cut q and divided by t, and this heat transfer must have occurred in a reversible manner. That's why the R stands for reversible. So how to calculate the change in entropy if a system travels along an irreversible path? So for that we have to replace this actual or irreversible path by a reversible path. So another diagram I will show. Suppose this is the irreversible path. This is initial state I. This is final state F. This is the actual or irreversible path. Actual or irreversible path. This is suppose TS diagram, temperature entropy diagram. So how to calculate the SF minus SI or delta S if the system has traveled from initial equilibrium state I to final equilibrium state F along an actual or irreversible path? Because we have just discussed that entropy is defined only for a reversible process. So how can we calculate in this case? So we have to replace this process by an imaginary reversible path. So this will be imaginary reversible path connecting two same states. Actually the system travels along this path. So but entropy cannot be defined along an irreversible process. So that's why we have to replace this actual or irreversible process by a reversible path, imaginary reversible path. Then only we can find out the change in entropy. Now I can calculate SF minus SI integral of dq by t reversible path, and this is equal to delta S of irreversible path. Since these are just point functions, entropy is a point function, so whether you travel along reversible path or irreversible path, the absolute values will remain same, just like volume or energy or any property. So there is no problem in calculating the change in entropy if the states remain same. Here the states, initial and final state, remain same. No matter whatever path the system may follow, the same change in entropy you will find out. So it is better to replace this irreversible path, because it is easy to calculate change in entropy by having a reversible path, because this d cut q by t is equal to ds is applicable only for reversible path. So you have to replace this irreversible path by a reversible one, and then you can calculate, and value will remain same. No matter whether you travel along reversible or irreversible path, change in entropy or change in any other property will remain same, because those are point functions, that they are independent of path. So this is how we calculate change in entropy of a system during an irreversible process or actual process.